Hello, everyone, again, and welcome to this week's Sets Online. My name is Mariano Ramirez, and I'm going to present today's talk. As every week, before we get started, we would like to thank our sponsorship from the International Association of Sedimentologists, which allow us to offer all the resources that you can find at setsonline.com free of charge. Make sure and check out our website and see what's going on this week in Sets Online and also in the upcoming events. And make sure to check what is coming up in the events organized by the Association of Sedimentologists. Today's lecture is going to be presented by Fulvio Franchi, who is an associate professor in the Department of Earth Sciences from the University of Bari in Italy. Fulvio received his bachelor, master, and PhD from the University degli Studi di Bologna, the University of Bologna in Italy. And his current research focuses on the interfaces between planetary sciences and carbonate sedimentology, with a particular interest for biogeochemical pathway and astrobiology. Today's talk is titled The Role of Sedimentology in the Characterization of Planetary Field Analogues. So Fulvio, the stage is yours whenever you're ready.
Thank you very much, Mariano. As you correctly said, my talk today is about sedimentology, but I want to present this science that is common to all of us from a different perspective, which is the perspective of a planetary scientist. I've been in Botswana for the past 10 years, and I recently moved back to Italy as a associate professor. So most of what I'm presenting today is going to be about Africa, because that's where I did most of my work. Anyway, before we start, I need to provide you a definition, because today we're going to do a lot of talk about terrestrial analogues. And this is the definition from the NASA website. Terrestrial analogues are places on our planet that are considered extreme, and extreme in terms of physical, chemical conditions. And for these peculiar characteristics, they become comparable to other celestial bodies, namely the Moon, Mars, and other planets. So they are crucial because they become laboratories that can be used as stand-ins for this celestial body that are not that easy to explore. So I want to highlight the word extreme, because the word extreme here is referred to life. We know, or we believe we know, the limits of life on our planet. They are normally set by temperature, by alkalinity, by pressure, oxygen levels, and so on. But in the last few decades, astrobiologists start to challenge the definition of limits and exploring these extreme environments in order to assess if life could exist outside our planet. But there is clearly more to it. So after a definition, a warning. When we talk about life, we need to consider it as a recipe. So we need ingredients, either on our planet or outside our planet. There is always a set of ingredients that is necessary for life to exist, or life as we know it. And these are organic compounds. Clearly, if we believe in life based on carbon, like us, nutrients, and liquid water, which is normally the media where life and all these ingredients are mixed. So mixed means that you need convection, so you need movement within this celestial body, and that means energy. And energy translates into a living planet. We know very well our planet is alive, so we are studying other planets to see if they were alive, if they ever been alive, or if they're still alive, and if they have all the ingredients for life. Now, what are terrestrial analogues? They are, as I said, places on our planet. There are different types of analogues. There are analogues that are called planetary analogues, normally very large scale structure, like impact craters, for instance, or volcanoes that mimic environmental conditions that we believe are present on other planets. There are analogues that are very relevant in terms of processes. And this is where sedimentology comes into the equation. We know sedimentary environments are all about processes. So there are certain environments that can lead us to understand what kind of processes are active on other planets. There are analogues that are important for their mineralogical composition, as they can tell us how mineral form on other celestial body. And then there are amongst my favorite astrobiological analogues. So those extreme environment where we can study the limits of life. And last but not least, the fun one, which are the engineering analogues. I'm saying fun because that's where engineers drop their rovers or part of their modules that are supposed to be part of space missions, and they check their performances on these rugged and extreme terrains. So today I'm going to focus mostly on processes and astrobiology, because again, the fil rouge is sedimentology. So we need to understand what is the role of sedimentologists in these planetary sciences. Now, how does it start? So how does planetary geology study start? Normally, it's from an observation of another celestial body. Right now we have plenty of free available data, but wasn't always like that. But anyway, we can have information from other celestial bodies, and our geological mind is built in a way that make us draw comparison every time we go in the field. We see an outcrop, we see some structures, and immediately, as trained sedimentology, we give a meaning to that structure. And that is basically the same that happened in planetary geology. Here on the left, you have a beautiful false color image from Jezero crater on Mars. And any sedimentology can say that in that picture, there is a satellite view of what looks like a relict or a fossil delta with the main trunk and the distributary channel, the interdistributary base, and the delta front, and so on. So the job is now to identify something on our planet that where we can run some experiments, some models, some even numerical models. So this is an humble example from one of our research. We look for fossil delta or fossil fans on our planet in order to run some experiments. So we start from the observation on the planet, and then we come back to Earth. Some starting assumption. As we said, we are here to talk about sedimentary structure and rocks and morphologies. So there are many morphologies that we observed on other planets, like my main experience is on Mars. Some of these morphologies, they have very interesting features, like in this crater, there are plenty of mounds which are settled on top of layered units. And immediately the sedimentology thinks, what is the process that can form this structure, and is water involved? We know that Mars was a warmer and wetter planet, and as sedimentologists, we are trying to prove that there are evidences for this previous phase of Mars evolution in the rock record. So again, the example of Jezero crater, where we have the satellite view of this beautiful delta. And the geologist here studying the strike and dip of the bedding in these images, they managed to identify foresets and bottom sets for any sedimentology on Earth that might indicate the presence of Gilbert-type delta. So an important sedimentological knowledge that is applied to another planet. So as I said, water is always the key factor, either as a surface runoff, like in the case of a delta, or as groundwater activity. One of the most important theories, and we're going to see it even later, about Mars is that there is or there was a deep aquifer that was coming to surface within craters. And within these craters, there was the formation of spring deposit, layer deposits, spring mounds, and all sorts of sedimentological features that became or will be target for future robotic missions. Again, on the geological processes, once you identify a feature or a structure on another planet that strikes your imagination, like in this case, this is from my PhD work. This is an aerial view of a mound. You need to start thinking about what kind of process could form such a structure. And you are on another planet, so you cannot run analysis, think sections, and so on. Not yet. So you need some ideas, something to compare them with. And you can start with different theories. For instance, someone believes that these are spring deposits, like spring mounds, exactly like those that we studied in a desertic area in central Australia. This is the Great Artesian Basin. Well, clearly on our planet, we have grass. On Mars, we are not expecting grass, but the upwelling of water, it's considered to be similar. The same exact morphology from other scientists is considered evidence from mud volcanism. Still, water is involved, but is a completely different process, a completely different scenario. So what they do, they get their own analog. This one is one specific work from one group. They targeted a mud volcano in Azerbaijan, and they start studying them and all their features as possible analog of the processes that formed these humps, these mounds on Mars. Now, another very important feature, if we stay within the sedimentology realm, it's methane. We know on our planet, methane is always linked one way or the other to life, either by methanogenic bacteria or methanotrophs. At cold seeps, you always have a community of chemiosymbionts. And therefore, the moment they spotted methane on Mars, it was in the early 2000s, the entire community shifted toward the research on potential analogues of this methane release on Mars, including myself during my PhD. So methane became even more popular in the last couple of decades because it has been found in the plume of a very tiny moon of Saturn, which is called Enceladus. We'll come back to this beautiful moon because it's believed to have an active core. So there is hydrothermalism, seepage, and all this sort of stuff. So clearly, a better understanding of how cold seep, maiden seep work on our planet can lead to a breakthrough also in planetary geology. Okay, so unfortunately for you, that was just an introduction. Because now I have to tell you what we are looking for. And the answer is very simple. As sedimentologists, when we work in planetary geology, what we are looking for are clues for water activity and, of course, of potential biomarkers. Well, biomarkers is probably not the right word, but evidences for extraterrestrial life. So finding evidence of water activity on our planet, it's quite easy. Basically, every sedimentologist deals with that. But to prove that it exists on other planet is not that trivial, not at all. So we look at specific environments. Not every environment can be considered an analog for planetary exploration. And what, for instance, looking at Mars, which again is the planet I worked the most, what are we looking in these extreme environments on Earth in order for them to be interesting for Mars geology? For instance, UV radiation. We need a place on our planet where there is a lot of radiation because Mars doesn't have ozone, we do. So we need a place that is heavily irradiated. We need a place where there is a lot of evaporation, potentially, because we know there was water on Mars, but all of a sudden that water was gone. So there are a lot of evaporites. And we need extreme condition in terms of temperature, pH, alkalinity, and so on. Now, because of time constraints, I decided to focus only on two examples, how sedimentology was applied to the study of Mars analogues. And these are from Morocco and from Botswana, one from my PhD and one from my latest field of research. And we're going to start from the Cascais in Morocco. The Cascais, they get their name from the pot where the couscous is cooked, and it's like this conical shaped pot. They are carbonate mounds found in the anti-atlas of Morocco. They are several tens of meters high, and they are all perfectly exhumed along this rocky hill. If you look for a documentary produced by National Geographic, which is called Mars something something, you will see that this landscape was used by the producer for the Mars base of the astronaut. So it is really a fascinating place. But speaking about science, these mounds, which are Devonian in age, they are settled on top of what we believe is a system of sedimentary folds. Some of them are perfectly chopped into half, and they have this beautiful internal stratification. And one of them has evidences for methane seepage. The ongoing theory says that, well, it's an old theory from the 90s, but we still believe it, is that the entire area is settled on top of cooling intrusion that fueled some hydrothermal activity that affected one way or the other these mounds. And this is relevant because we know that hydrothermal activity can sustain communities of extremophiles and hemoautotrophic community. And these are probably places, talking about the hydrothermal vents, where life on our planet emerged. So hydrothermal activity is extremely relevant, although it's quite difficult to prove, especially in the old fossil record. There are some mineralogical evidences, some fractures, some particular type of fossils, but it wasn't particularly convincing here. So the parallelism is with black smokers, deep marine vents where hot water with a lot of nutrients is discharged into the ocean, and where bacteria can not only thrive, but they can also be preserved into the rock record. Remember that as geologists, we're looking for rocks or sediments. So that's the same we're looking for on other planets. And once again, active vents have been hypothesized also on other celestial bodies like Enceladus, for instance. So looking at hydrothermal vents and cold seeps became extremely relevant in the past few years. Now, in the case, a lot of paleontological and geochemical studies have proved the presence of methane seepage. I already explained why methane seepage is important. Not that we are going to look for chemosymbiotic bivalves and other macroinvertebrates on Mars. Not at all. I'm saying this because I want to send a message that as sedimentologists working on this field, you still have to do the normal work of any sedimentologist. So you characterize your field analogues paleontologically, geochemically, and we will see also geophysically, in order to lay the foundations for a better interpretation of the environment. And anyway, it's important to highlight the presence of methane because, again, this kind of environment can harbor chemosymbiotic organisms, and some of them can be fossilized. Here we can see some evidences of chemosymbiotic organisms in the cascades that gives us hope to find, well, not hope, sorry, that indicates that these are suitable geological matrix for the preservation of extremophiles, so bacteria that live in extreme environments. So to conclude with the cascades, we have these conical mounds which are formed along fractures. So they were linked to fluids. Well, clearly they form underwater as every carbonate mound, but on top of that, they were linked to fluids. So they were either cold seeps or hydrothermal vents, which in either case is interesting because of the type of biota that can live in this environment. And because of their carbonatic nature, they are very good in preserving microbial fossil. But first and foremost, they are very, very similar to the morphologies that were identified on Mars. So that allows us to work on a theory that can point towards similar processes, similar genetic processes. Okay, so the second analog that I'm going to present you today, sorry, I have a bit of cold. Anyway, is completely different. Now we are talking about an quaternary salt lake in Botswana, which is called the Makgadikgadi, in the Makgadikgadi Basin, is in central northern Botswana. And it was linked to the Okavango Delta. And now it hosts one of the largest evaporitic lake system in the planet, our planet. And this place, it's at 1,000 meters above the sea level. There is no shadow. Trust me, I've been there. So the surface is constantly irradiated by UV. So whatever lives there needs either a thick skin or metabolism that allows life under strong UV radiation. It's an hypersaline environment, so there are evaporites. And why are evaporites interesting? Well, because they were identified also on Mars, and especially hydrated minerals were identified by satellite missions on Mars. There are some beautiful layered deposits, as you can see in this gray color image, where there is an alternation of different type of hydrated minerals. Again, why are they relevant? Because on our planet, they normally form when water evaporates. And in this type of highly evaporative environment on our planet, there might be chance to find extremophiles. Now, there are a number of minerals, I'm not going to mention all of them, that became target of planetary geologists. Here you see a team from France studying silica, opaline silica, other hydrated mineral have been identified in deltas on Mars. Geologists, sedimentologists are now busy building a spectral database of similar occurrences on our planet in order to interpret data coming from Mars. And what is also important is to petrographically characterize this type of sediments. You see here on the top, there is some spherulithic chalcedony that forms under this evaporative condition. But what is more interesting is that sediments and concretion within these evaporative lakes, they host a huge amount of microbial signature. So in the top right, you see some evidences of what is called halophilic endolithic bacteria, so bacteria that live inside microorganisms that live inside the crystals of halite. And at the bottom, you see some ACM images of filaments of fungi and cyanobacteria, that live on in the Makgadikgadi salt pan. So these are organisms that can survive not just the UV radiation, but also the salinity, the evaporation, and all sorts of harsh conditions. But again, what matters at the beginning is always a morphology. I normally show this slide to my students, and I ask them which one is Mars and which one is Earth. And well, because we don't have interaction here, I can tell you that the one on the far right is the one from Botswana, from the Makgadikgadi. And we are looking at the same type of structure. These are mounds, layered mounds, but on two different planets. A and B are from Mars. C is from Botswana. And the striking resemblance and also the size of this morphology, so the one from Earth is similar to the one on Mars, convince us to run all sorts of experiments of those mounds. We wanted to know and to have as many information as possible. And particularly, we wanted to understand what process is involved in the formation of these mounds that are so similar to the Martian ones, and what is the role of water. Remember, we are in a dry lake, so the only water can come from underground. So we went on these mounds and we ran some geophysical survey. Now, I spare you all the details. You can read the paper if you want. But we found some evidences of not groundwater upwelling, but something that we never considered before, that was simply moisture. So these mounds probably exist only because they pump moisture from the phreatic zone and they become more resistant to the wind activity. And that is something that we can also apply to Mars, which is gigantic desert with a lot of wind activity. Let me skip this one. So there are also, as I showed you, plenty of evidence for drainage system on Mars. So the entire scientific community is busy looking for analogies with drainage system on our planet. So we have something that is called inverted channels. Very briefly, on Mars, there are these positive reliefs, and we believe that these are the coarser material, the channel field deposits that are less erodible than the overbank deposits. So during the billions of years of erosion on Mars, the floodplain deposits were removed to leave a positive morphology characterized by these channel fill deposits. And clearly, this is something that can happen also on our planet. And in fact, we identified something similar in Botswana, where there is a fan delta that goes straight into the salt lake. And this fan delta has some channels. And when you look at these channels, they are, well, they don't have the same size as the Martian one, but they are inverted channels. So they become positive morphologies. So once again, we have the same process, potentially the same process on two different planets. Also, in front of this fan delta, we identify what we normally call polygons. So these are polygonal fracture. We normally call them mud cracks in sedimentology, but polygons is fancier. And these are features that are very common in every evaporatic environment on Earth, but they were also identified on Mars. At the bottom of the slide, you see some images from Mars. So this is actually a work that one of my PhD students is doing into the pen, because once again, similar structure might lead to the conclusion that they were formed by similar processes. I'm almost done, but I want to show you something completely different that we've done in this salt lake, and that was to test an equipment, an instrument with some engineers from INTA, from Spain, that have an ongoing mission on Mars, and they wanted to test their instrument, basically to study dust devils in a place with a lot of dust. So I invited them over in Botswana, and we tested an instrument that is actually right now on a rover on Mars, and we tested it under analogues condition on our planet. So in conclusion, why the Makadikadi is considered a good analog? First of all, for the radiation is not as much as Mars, but still to live there, you need to adapt. It's an hypersaline environment like the so-called playa deposits on Mars. It has very peculiar morphology, which are similar from a sedimentological point of view and a morphological point of view to the Martian ones. There is groundwater upwelling and evaporation, which are two processes extremely relevant for Mars. Strong aeolian erosion, again, a very relevant process on Mars. There are fossil deltas and channels, and most of all, everything that you see here, these kind of humps that you see, these are all colonies of extremophiles that are living inside the soil crust. So biologists and astrobiologists are busy studying how these microbes and fungi, they can survive in such environment. And of course, they need a sedimentologist to help them characterize the environment before they can run their own laboratory experiment. Okay, so these are the analogs that I showed to you. To analogues, the Morocco, the Keskes on the top left, and the Makadikadi on the right. And we are just concluding here by saying, normally what we do in this job is whenever we see similar morphologies, we assume they are formed by similar processes, and that's where the science begins. That's where we get in the field and we start proving or disproving our theory that similar processes can give you, so similar morphologies are given by similar processes. With this, I thank you, grazie, and Kale Boga, and I invite you to participate at our session. I know that we are all going to the EIS meeting. I'm also going, but in June. But in September, we have a Europlanet meeting where we're having a session, or 3 sessions actually, on the geology of planetary geology. And if you are interested and if you're working in the field, I invite you to submit your work so we can expand our community of sedimentologists on Mars. Thank you very much.
Wonderful, Fulvio. Thank you. Thank you very much to you. That sounds like a super interesting conference, actually. Okay, so please remember, everyone, now we are open for questions. So remember to write your question in the chat and then be sure to send it to everyone. Also, please remember to write your name and where are you watching at. In the meantime, I have a couple of questions for you, Fulvio. So you mentioned some of the minerals that they have been described in Mars, like especially with not with the rovers, but with the satellite observations. So my question is, do you know if the rover has been able to analyze some of the minerals that they found in the evaporates in Mars?
Yes. The rover, the rovers plural, they were equipped with plenty of mineralogical equipment, cameras. There is one Raman spectroscoper on Mars. So yes, they analyze and they confirm some of the minerals. The problem is the scale. Sometimes when you have a satellite image, you have a larger scale, so you can pick up differences in the mineralogical composition. When you are on the ground with the drill or with the spot analyzer, it becomes a bit more complex to find the right spot.
But were those minerals like similar to those found here on Earth?
Yes, don't ask me the list of minerals though, because I'm not prepared on that. I need to.
No, I'm not gonna do that. Don't worry. Okay.
One I can confirm is are the polymorph of silica. They became extremely interesting because they were unequivocally identified also on Mars. So those one became extremely hot topic for analogues on Earth.
Wonderful. We have another question from Monica Rasmussen. Monica said, thank you, great talk and very interesting. She's watching from the USA, but working with the INAF in Rome later in this year. So, and she said, you mentioned wind activity and erosion. When you consider these comparisons, how do you extend weathering and erosion assumptions back billions of years?
This is a tricky question from someone that knows the business. Yes, it's very true. That is one of the main issue that we are facing as geologists. We can barely imagine what 1 billion of year of erosion could do on our planet, because simply it never happened, or if it happened, we don't have a record on our planet. So I think, and I might sound well, I think that we don't have an analog for that. We only have models that can be built on observation on our planet. So that is more, at least as far as I know, and as far as, in my opinion, it's more getting into the modeling in the prediction field rather than observation on analogues. Because simply, maybe I'm wrong, but as far as I know, there is no place on our planet that can show long millions or billions of years of erosion. It's simply impossible to find.
Yeah, maybe we should go to some of the oldest craton in which there are like less sedimentation or more erosion, of course. But yeah, oh, actually, Monica says, thank you, perhaps Central Australia. And yeah, that sounds reasonable. What do you think, Fulvio?
Yes, but I've been to Central Australia, but looking for the spring deposits, so very, very recent rocks, because again, I was focused more on the what we call the aqueous processes, so the link between water upwelling, minerals, precipitation, and biological activity. Certainly, what she's bringing up is one of the critical aspects of this field. We need to consider billions of years of erosion, and it's not easy. There
Yeah.
are way arounds, but I don't think we have time to discuss about those way arounds, shortcuts.
Yeah, it's pretty tricky, but it's part of it's part of being a geologist. I mean, you have to deal with the lack of information as well, sadly. So I have another one which is more related to the models that you were mentioned. So, I mean, what we can do here on Earth is, of course, like characterize geomorphologically like a lot of things. But then when we scale them and when we model them and try to compare with Mars, we find like, of course, some challenges. Some of these challenges probably are related to the scale, but also some of the other challenges are like related to time, as Monica said. So I think that my question is more related, like, do you think that some of the sedimentary rates in terms of erosion, deposition, etc. in Mars can be comparable to those that we see here on Earth?
Okay, so when it comes to, for instance, rivers and deltas on Mars, we believe, well, not me, I mean, it's written that that activity occurred in narrow, well, geologically narrow window of time. So in that case, if you consider the single process or the single morphology of structure, then it is comparable to what we see here. So always remembering that atmosphere and all the physical parameters of Mars are not the same of our planet. But if you consider that, then looking at the delta, for instance, or at other morphologies like that, it is reasonable to think that they form over the same period of time. The size sometimes is tricky because everything on Mars looks bigger, but one of the structures I showed you, the one where I focus the most, are conical mounds, and I showed the scale of the mounds we study on Earth. It's basically the same as the mounds we study on Mars. So clearly, you can't avoid by acknowledging that they are similar. If they were formed by the same process in the same period of time, we don't know. But again, these are just hypotheses. We don't know. We will know nothing for sure.
Yeah. No, I mean, it's fascinating. It's fascinating. I think it's gonna be a game changer if at some point we are able to bring some of the samples back. Not for the geomorphological aspect, of course, but from the geochemical, mineralogical, compositional aspect, that would be a game changer.
I'm afraid that's what people care the most is about extraterrestrial life. So most of these missions are astrobiological. So right now there is a lot going on about preparing the human mission. So how to harvest resources, how to like survive on Mars or on the moon. But up until now, the prevalent question was how do we find life? So, and when we have a sample from Mars, how do you know you are using the right techniques?
Right.
That is what we're working on.
That's another world of questions. We have another one from Monica, and she says another tricky question. How does the much lower atmospheric pressure on Mars impact on sedimentological processes?
Monica is killing me now. Huh? She's asking all the difficult questions. Well, I mean, that goes together with the erosion is a question mark that we are trying to solve with models. I'm not a modelist, so don't expect me to explain you how the models work. I'm a geologist like you. I work in the field, but there are models that consider the different atmospheres because we believe that Mars once had an atmosphere, so probably it wasn't always like right now. So right now we can measure atmospheric parameters and we can tell exactly how sand moves and how dunes are formed right now. But in order to explain what we find in the rock record, we only have assumptions on how it was. So we are running models. Again, people much better than me do models. I simply take samples from the field. Monica, people at enough are the good ones for this. That's what they do the best.
Yeah, I mean, but also I mean with the dune fields that we see currently in Mars, they looks like, I mean, they have like shapes and everything pretty similar to what we can see here on Earth. Of course, not water, right? But I mean, those sedimentological processes seems to be working like in the similar way.
Well, one thing that I also teach in class is the physics behind sedimentary bed forms. Like, you know, when you study the hydrodynamics, Bernoulli effect, and all this. I mean, this is physics. So, in considering all the change in atmosphere and parameter, like Monica pointed out, but it's just physics. So it's reasonable to assume that if you have a turbulent current, you might have cross bedding even on Mars. In fact, there are plenty of sedimentologists that published beautiful pictures from the rovers where you see cross bedding. They're pictures taken from afar from the outcrop, but you can see cross bedding. Somebody sees two different currents going one side. I mean, but for sure, if you look at the images that we are getting from Mars, there are many processes that can be identified.
Yeah, absolutely true. Okay, we have another question from Trajas Kasi. Hello, my name is Trajas and I'm from Botswana. I have a question for you, my great supervisor. Why do we care to search for evidence of life beyond Earth, particularly on Mars? Do you believe that the origin of life could be Mars?
Hi, Tras. Yeah, she's my PhD student. But I didn't ask her to ask me this question. She likes to challenge me. No, that's a good question. Okay, why? Because, and that's something that I personally do on Earth, that can tell us how life evolved on our planet. If we, I didn't mention it, sorry about that, but we believe that life evolved at the same time on the two planets. So more or less, let's say in the Archean, on the two planets, they were similar conditions. So if we understand how life in extreme environment like Mars evolved, maybe we can get it answer also on our planet. The truth is that this kind of science is pushing the boundary of technology, so it's giving us more and more refined tools for understanding our planet. Why Mars? Because I believe is the one where we got more striking evidences of similarity with our planet. And I don't know if I believe that life came from Mars. She's probably referring to panspermia or to one of those theories. I don't know if life came from Mars. I do believe that there is or there was life outside our planet. Statistically,
Probably.
it must be. Maybe not Mars. I don't know. But even if we find nothing, the technology that we developed to get to answer this question, it's worth all the investments. Instruments are much smaller because we have to send them on Mars. We are refining our understanding of biology and geomicrobiology. We are refining our understanding of mineralogy. So we're pushing the boundaries of geoscience. So it's not just for the fun of looking for life outside our planet, but it's a scientific challenge that we should all embrace. And it pays your PhD, so.
Yeah, fascinating, Fulvio. Thank you very much. I mean, I think this is a super interesting topic, and we can keep talking all day long. There are too many things to unravel there. So Monica and Trust say thank you very much. So I'm gonna thank you all for coming to this very interesting talk today, and of course, thank you, Fulvio, for being here today. Don't forget to get in touch with the Sweet Sets Online. We have a newsletter, and see you all in Aberdeen.